What we're going to talk about right now is exponential functions, and specifically using a description or a word problem to write an exponential function or equation. And so a couple of things you want to make sure before we even start that you understand. First of all, you absolutely need to know what an exponential function looks like. It's going to be in this format: a times b to the x, and it can be written either with a y like this, or in function notation. Now, a is just your initial value. So basically that means the number or the value that you're starting with. So that's the key thing. It's the starting or beginning number, okay? And then b is your growth rate. If we were finding this from a table or a sequence, the growth rate is the exact same thing as the common ratio. However, here the growth rate, and it can be a little confusing. It's the growth rate, but it doesn't always have to be growing. If it's going down or decreasing, then we're talking about exponential decay. But b is still the growth rate. So the growth rate in this case will be 1 plus or minus the percent in terms of a decimal. Now, one of the examples that we're going to do today will be slightly different, but this is the basic format. It'll be 1 plus or minus the percent. And like I said, you have to convert it to a decimal first. So I'll give you a couple of examples. First one, and these are both going to be real life examples. This happened. Okay, in 1800, the population of the United States was 5,300,000 people. And the population was growing at a rate of about 3.15% per year. So that's the annual growth rate. Now, you write an exponential equation that represents the population growth in the USA during the 1800s. It wasn't this rate the whole time, but for most of the 1800s up until 1870, so from 1800 to 1870, it was pretty close to that. Then from the Civil War, it dropped a little bit to about 2%, and then after that, it started to drop a little bit as well, as we get closer to the 1900s. In the 1900s, the rate dropped a little bit more. So these are actual numbers. In 1800, the population was 5,300,000, and the population was growing at 3.15%. So we need two things. We need the initial value, remember that's your starting point, and we need the growth rate. Now, the initial value is not the beginning of the United States. It's when we started counting. Now we're counting. That's when we're going to start counting in 1800. But it's not this number. It's how many people there were in 1800. So at the beginning of our time frame that we're counting in 1800, there were 5,300,000 people. So that's what our initial value is. Like that. Now the growth rate is going to depend upon the percentage rate right here. So the first thing you have to do is convert to a decimal. So 3.15% is equal to, we move the decimal place 2 places, remember 1, 2, we'll insert a 0 here and a decimal place there. like that. So it'll be 0.0315. So now, if it's growing, if it's getting bigger, we're going to add that. If it's getting smaller, it's decreasing, we're going to subtract that from 1. So, like I said, remember it's 1 plus or minus, and here it's going to be adding. So we're going to add. So our growth rate B will be 1 plus 0.0315. So B will be equal to 1, 0.0315. So now we've got two numbers that we absolutely need. And if we have those two numbers, it's easy because all we do is plug it in. Remember what our exponential functions or equations look like? They look like this. A times B to the x. That's A. So we plug it in. 5,300,000 times, and I always like to use parentheses especially when you have kind of a messy number like this, long decimal. It separates a little bit easier and makes it easier to see. So 5,300,000 times 1.0315 raised to the x power. And that's what the function looks like. Now, if we want to know, so in 1800, the population was 5,300,000. If we want to know what it is in 1810, okay, we're not going to use this number. We're going to use how many years went by from 1800. So from 1800 to 1810 is 10 years. So to find out the population in 1810, we're going to do it like this. 5,300,000 times 1.0315 raised to the 10th power. And then you just calculate that. And we have, and I'm sorry about the reflection, but we go 5,300,000 times 1.0315 x to the y 10, and we have 7,227,168, and it doesn't make sense to have decimal places for people, does it? So let's just round that up to 9. 7,227,169 people. Now, of course, that's not exactly right. You can't, I mean, it might have been 70 or 200. Anyway, that's pretty close. We'll call it 7,200,000. 7,200,000. Your science teacher, your science teacher wouldn't like it if you take that many significant figures out. So don't do that. You only have 2 here. I've got to have 2 here. Okay. Now the next example is something that, now I guess people don't take aspirin as much. It's ibuprofen or something like that. But aspirin is a really common medicine, and in medicine, it's very common to talk about something called half-life. Now, what the half-life is the amount of time that it takes for something to decrease by 1/2. So if we start off with a 10, half-life, it would be at 5. It would go from 10 to 5. Now, the amount of time that a drug stays in your system varies. It varies by person, but it also varies by the medicine. medication, whatever. Some things stay in your body much faster than other things. So for aspirin, it's about 3 hours for small doses. And so one adult aspirin is typically 325 milligrams. For larger doses of aspirin, it'll stay in your body for longer for various reasons. But for small doses, it'll stay in for about 3 hours. So the question is, how much aspirin can be expected to remain after 12 hours? Now, in this case, we'll start off with exactly the same as we did before. Okay, we want to find out two things. We want to find the initial value, so that's what are we starting with? Well, what we're starting with in this case is somebody takes some aspirin, and then as soon as they take that aspirin, when it gets into their bloodstream, they have 325 milligrams in their bloodstream. So that's what we're starting with. So that's A. Okay, now in this case, it's decreasing by, it's being cut in half. So the easiest way to think of this is just, we're starting with 1, and then we cut it in half. We're dividing it by 2, right? So remember, B and the common ratio, they're the same. So we're dividing by 2, that's the same as multiplying by 1/2. Remember, multiplying by a fraction is the same thing as dividing by its reciprocal. So B is equal to 1/2, and now we can plug it in, and we write it like this. A is 325 times 1/2 to the x. So that's what our equation looks like. The only tricky thing about this is that we're not counting years, right? We're counting 3-hour chunks. So every 3 hours it goes down by 1/2, not every hour. So that's one thing you have to be a little careful with. How much aspirin can be expected to remain after 12 hours? Well, if you think about that, 12 hours would be in groups, if we're doing it in groups of 3, would be 4 groups of 3, right? So it would go, for us to go 3 hours at a time, that's 4 different time frames. So we're not going to count this as ones. We're going to count this as the number of 3s. I don't know. I hope that isn't too confusing. So for 12 hours, we're not going to use 12. We're going to use 4 3s. How many? So we got 325, 1/2, and then now we calculate. $325 times, I can just write it as 0.5, but I'm going to write it as 1/2. That gives us 0.5. Y to the x4. So we would have 20.3, so about 20 milligrams. Okay. So remember, this is 4 times 3, right? So this is one time chunk times 4, and that's what gives us our 12.